Today we are going to discuss Vandermonde Determinant. This determinant comes up in various applications. So we consider the following n by n Vandermonde matrix. So the first row of this matrix is filled with ones. In the second row we put a1, a2, ... an. In the third row we put a1 squared, a2 squared, and then an squared. In the next row we'll put the cubes of these elements, and so on. So then second last row will be a1 to the n minus 2, a2 to the n minus 2, an to the n minus 2. And the nth row of this matrix will be a1 to the n minus 1, a2 to the n minus 1, up to an to the n minus 1. So this becomes an n by n matrix. And what we want to do is we want to compute the determinant of this matrix. So this matrix is called the Vandermonde matrix, and the determinant of this matrix is called Vandermonde Determinant. And we will denote it as Vn of a1, a2, an. We state the following theorem, that the value of this determinant, so Vn of a1, a2 up to an, is given by the formula. So we take the product over I and j that range from 1 to n, and I being less than j. And here we take aj minus ai. So for example, if we take n equals 3, then here we have the following determinant. We have 1, 1, 1, a1, a2, a3, a1 squared, a2 squared, a3 squared. And then this formula tells us that the value of this determinant is equal to a2 minus a1 times a3 minus a2 times a3 minus a1. So let us give the proof of this theorem. So we are going to prove this theorem by induction. On n. And the basis of induction is trivial, because if we take V1, so this is a 1 by 1 matrix with entry 1, so V1 is equal to 1. But then here, because I is less than j, so there are no pairs I less than j that are between 1 and 1. And so this product in the case n equals 1 is an empty product. And the empty product is equal to 1. So empty product is equal to 1. This is our convention. As empty sum is equal to 0, then empty product is equal to 1. So next we want to do the step of induction. So we assume that Vn minus 1 is given by this formula. And then we're going to show that this formula holds for Vn. We're going to compute the Vandermonde determinant by applying elementary row operations. And we know how the determinant transforms under elementary row operations. We're going to start with the last row and then move up in this matrix. So our first elementary row operation that we apply will be new row n is row n minus a1 times row n minus 1. So this is a type 1 elementary row operation, so it does not change the value of the determinant. And so here only the last row changes. So I'm going to write down only the last row, and all the previous rows are unchanged. In the first position, so if we take a1 to the n minus 2 and multiply that by a1 and subtract from this a1 to the n minus 1, then we're going to get 0 in the bottom left corner. In the next position, we're going to get a2 to the n minus 1 minus a1 times a2 to the n minus 2. And in the last position here, we're going to get an to the n minus 1 minus a1 times an to the n minus 2. Next, we're going to apply elementary row operation to n minus first row. We say row n minus 1 new is row n minus 1 minus a1 times row n minus 2. And again, in the first column, we're going to get 0, because here we will get a1 to the n minus 2 minus a1 times a1 to the n minus 3. And then in the next position, we're going to get a2 to the n minus 2 minus a1 times a2 to the n minus 3, and so on. And in the last column, we're going to get an to the n minus 2 minus a1 times an to the n minus 3. And the upper rows are so far the same as in the original matrix. And again, so the determinant did not change. So then we move up and we apply elementary row operation. Row n minus 2 prime is row n minus 2 minus a1 row n minus 3. And so on. So we just keep going up like this. Then we will say that row 3 new is row 3 minus a1 times row 2. So let us see what will be the result. So in the first column, we're going to get 0 because we have a1 squared minus a1 times a1. So here we're going to get 0. Then in the second position, we're going to get a2 squared minus a1 times a2, and so on. And in the last column, we're going to get an squared minus a1 times an. And finally, we say that new row 2 is row 2 minus a1 times row 1. So then in the first position, again, we get 0. Then here we're going to get a2 minus a1. And in the last column, we are going to get an minus a1. And we don't change the first row at this stage. So then we get a new matrix that looks like this. And the determinant of the original Vandermonde matrix is equal to the determinant of this new matrix, because all the elementary row operations that we have applied are all of type 1, and they don't change the value of the determinant. Now, let us look at the new matrix. So what can we see here? So we see that the first column has lots of zeros. And thus, we can treat this as a matrix with a corner of zeros. And so then we see that we have a factorization of this determinant. So this determinant is equal to determinant of this 1 by 1 matrix, which is 1, times the determinant of this matrix of size n minus 1 by n minus 1. So here we have the determinant of a matrix with a corner of zeros. And so we get that this determinant is equal to the determinant of n minus 1 by n minus 1 matrix, so let us write it down. So the first column is going to be A2 minus A1, then A2 times A2 minus A1, then the next will be A2 squared times A2 minus A1, dot, 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 and the last entry will be A2 to the n minus 2 times A2 minus A1. And so the last column of this matrix will be AN minus A1 times, well, next one will be AN times AN minus A1. Then we'll have AN squared times AN minus A1, dot, 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 and AN to the n minus 2 times AN minus A1. We know how determinants behave under elementary row operations. So, for example, if a certain row has a common constant factor, then we can pull out this constant factor out of this row, and we also pull it out of the determinant. But we also know that determinant of the transpose matrix is equal to the determinant of the original matrix. And the elementary row operations on a matrix correspond to elementary column operations on the transpose. And because the determinant does not change under the transpose, this tells us that we also can perform elementary column operations on the matrix. And we know how determinant changes under elementary column operations. So, for example, if we switch two columns, then the determinant will change sign. In this case, so what we have is that each column will have a constant common factor. The first column has a common factor of A2 minus A1. The second column will have a common factor of A3 minus A1. And the last column has a common factor of AN minus A1. So what we can do is we can pull out these constant common factors out of the determinant. And what we get is we will get A2 minus A1 times A3 minus A1 times dot, 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 AN minus A1 times the following determinant. So in the first column, we're going to get 1, A2 squared, dot, 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 A2 to the n minus 2. Then we'll have 1, A3 squared, A3 to the n minus 2. And so on. We'll have 1, AN squared, AN to the n minus 2. And so what we see here is that here we will get the Vandermonde determinant again, but now of size n minus 1. This calculation tells us that Vn of A1, A2, AN is equal to the product where j goes from 2 to n, Aj minus A1 times Vn minus 1 of A2 dot, 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 An. But here we can apply our induction assumption. So by induction assumption, we have a formula for the Vandermonde determinant of size n minus 1. So this will be equal to the product j goes from 2 to the n, Aj minus A1 times the product. And now here we will have the indices. So because here we don't have A1, we have things from A2 to AN. So here we will have I less than j, and they will be from 2 to n. And we will get Aj minus Ai. And now we can see that we can combine these two products. So this term will simply correspond to I equals 1. And so then we will get the product. Now I less than j, now between 1 and n. aj minus a1, ai. And this is exactly the formula that we had to prove. So one corollary that we want to mention is the following, that if these numbers a1 through an are distinct, so this means that ai is different from aj for I different from j, then the corresponding Vandermonde determinant is not equal to 0. And indeed, so this follows immediately from this formula. So if these AIs and AJs are all distinct, then all these factors are going to be non-zero. And since we're working over a field where we don't have divisors of 0, the product of non-zero factors is non-zero. And we know that non-zero value of the determinant tells us a lot about this matrix. So for example, this matrix will be invertible, and the rows or columns will be linearly independent. As one of the applications of the Vandermonde determinant, let us look at the topic of polynomial interpolation. We know that if we are given 2 points on a plane, then we can draw a line that passes through these 2 points. So we can write y equals ax plus b. Now, what if we are given 3 points on a plane? Well, clearly, it's not possible to draw a line that passes through 3 arbitrary points. But can we draw a parabola, y equals ax squared plus bx plus c, that will pass through the given 3 points? Well, it turns out that this is possible. And even more, so this claim can be generalized not just for the 2 points in case of a line or 3 points in case of a parabola, but for a general case of n points on a plane. So we have the following theorem. Given n points x1, y1, x2, y2, xn, yn, with distinct x coordinates, so this means that xi is different from xj for I different from j. So there exists a polynomial p of x of degree at most n minus 1. So p of x is equal to c0 plus c1x plus c2x squared plus cn minus 1 x to the n minus 1, such that the value of this polynomial at the point xi is equal to precisely yi. So for I, for all I from 1 up to n. So this means that if we consider the graph of this polynomial, so y equals p of x, then the graph of this polynomial will pass through all of these endpoints. And it is natural to consider this restriction that xi must be different from xj. So this means that we are not allowed to have 2 points on the same vertical line, because here we're trying to interpolate these points with a function, and a function cannot assume two different values for the same value of the argument. So this polynomial is called interpolation polynomial. And the procedure of finding a curve that passes through given endpoints, so this procedure is called interpolation. Interpolation has vast applications ranging from astronomy to computer animation. In astronomy, you take observations of some asteroid that you record every night, and then you have to connect these points that correspond to your observations with a curve. And in computer animation, you represent moving bodies with meshes of points. And then you need to smoothly connect these points together to form a surface. And again, so two-dimensional version of interpolation is used for that. Let us give a proof of this theorem. So we treat the coefficients of the interpolation polynomial, so C0, C1 up to Cn minus 1, as unknowns. How can we solve for these unknowns? The constraints that we have is that P of x1 must be equal to y1. So what does this mean? So this means that C0 plus C1 x1 plus C2 x1 squared plus Cn minus 1 x1 to the n minus 1 is equal to y1. Then the next condition is that P of x2 must be equal to y2. So this gives us that C0 plus C1 x2 plus C2 x2 squared plus Cn minus 1 x2 to the n minus 1 is equal to y2. And so on. So the last condition will be that P of xn is equal to yn. So this gives us the equation C0 plus C1 xn plus C2 xn squared plus Cn minus 1 xn to the n minus 1 is equal to yn. Now, here we know the values of y's, and we know the values of x1 through xn. So the unknowns are C0, C1, and Cn minus 1. And what we see here is that we get a system of n linear equations on CI's with n unknowns. Let us write down this system of equations in a matrix form. So we have a matrix times the column of unknowns, which is C0, C1, Cn minus 1, is equal to the right-hand side column, which is y1, y2, yn. Now, what is the matrix of coefficients? So here the first coefficient is equal to 1. Then we have coefficient x1, x1 squared, x1 to the n minus 1. Then for the second equation, we have 1, x2, x2 squared, x2 to the n minus 1. And the last row of this matrix is 1, xn, xn squared, xn to the n minus 1. And what we see is that the matrix of this system of linear equations is the transpose of the Vandermonde matrix. And because all xi's are distinct here, right? So we have this condition. So this tells us that here we have a square matrix with a non-zero determinant. So and since the determinant of the Vandermonde matrix is not equal to 0, so we conclude that this system of linear equations has a unique solution. And this proves the claim of this theorem. So since we are able to solve for the coefficients of this polynomial, so this will tell us that there will be a polynomial of degree at most n minus 1, such that for each I, p of xi is equal to yi. So this means that the graph of this polynomial will pass through all of these endpoints. It turns out that we can give an explicit formula for the interpolation polynomial. So this is called Lagrange's interpolation formula. So the claim is that this interpolation polynomial p of x can be written as the sum I goes from 1 to n yi times the product of j goes from 1 to n, but skipping the value of I, x minus xj over xi minus xj. To see that this formula works, so we just consider the term here. So let's call fi of x to be the product over j different from I, x minus xj over xi minus xj. Now, what will be the value of this polynomial at the given points? So, for example, so what is f2 evaluated at x1? So the claim so that this will be equal to 0 because this polynomial has a factor of x minus x1. Right? So these polynomials have factors x minus xj for all j different from I. So this polynomial f2 does not have a factor x minus x2, but it has a factor x minus x1, x minus x3, and so on. And so what we see is that fi evaluated at xj is equal to 0 if j is different from I. And when we substitute here x equals xi, then all these factors will become 1. So this means that we'll get value of 1 if j is equal to I. And then our polynomial p of x is equal to the sum I goes from 1 to n yi times fi of x. And so then when we evaluate p at the point xj, then what we get in this sum, so all polynomials fi's evaluated at xj will become 0 except for the term when I is equal to j. And so what we will get is we will get yj times fj evaluated at xj, and this polynomial has value 1. And so the result we will have yj. And this will be true for all j from 1 to n. And so what we see is that this polynomial has prescribed values at prescribed points. As an example, when n is equal to 3, then the Lagrange interpolation polynomial looks like this. So we'll have y1 times x minus x2 times x minus x3 divided by x1 minus x2 times x1 minus x3 plus y2 times x minus x1 times x minus x3 over x2 minus x1 times x2 minus x3 plus y3 times x minus x1 times x minus x2 over x3 minus x1 times x3 minus x2. So note that the denominators here are scalars, and so these are non-zero constants. And so the polynomial structure only comes from the numerators, and we see that this is a sum of 3 quadratic polynomials, and as a result it has degree at most 2. And so the first term will have value 1 when x is equal to x1, and thus it will provide the value of y1. So this will say that p of x1 is equal to y1. And at the point x1, the final 2 terms will vanish, because here we have a factor of x minus x1, and here we have a factor of x minus x1. So this polynomial is designed in such a way that it has prescribed values at prescribed points.